Let's continue our discussion further and let's try to calculate some physical observables in the 5-4 theory and see what we get. So let's say we try to calculate a physical mass of the particles in this theory, okay, and see what happens. So you remember that the action in 5-4 theory is integral d4x half del mu phi minus half m square phi square minus lambda over 4 factorial phi to the 4. Okay, where m is some mass parameter. So if I want to calculate physical mass, that physical mass will be expressed in terms of these parameters m square and lambda, right? Because all observables will be functions of these parameters that appear in the action. So the physical mass, which we have been calling mp, will be a function of m and lambda. And so let's see. So I should look at 2-point function and find out where the pole of this 2-point function is. And you remember that the location of the pole is the physical mass. Okay. So to lowest order is this propagator, which is just I over p square minus m square. So m physical to lowest order is just m. Okay. Now we want the effects of quantum field theory in finding out what the physical mass is, because this prediction is prediction based on a free theory, right? Because we have not included any interactions. This is a simple propagator which doesn't include any interactions. So let's include interactions, and then you have this term. Okay, so I have to calculate this loop and then take into account its contribution. Okay, and then we have these other diagrams as well. We have seen this earlier in this course, or maybe in the previous course, I don't remember where we did. And there are all these diagrams, right? We have to sum up all of these, the infinite of them. And we have already seen that such integrals diverge. So if you take this one, it will give you d4L, where L is the loop momentum. Let me draw this clearly. I assign the momentum this way. External momentum P is entering. But you see at this point when it enters, okay, there is no external momentum that enters into this propagator, right? Because you have written down L for the loop momentum, and momentum conservation doesn't allow anything else entering into the loop, because whatever enters in exits here. So you see here is L going out, and at this vertex from this side L is entering. Okay, so momentum conservation says that P cannot enter into the loop. Okay, this is very special for this kind of vertices. Anyhow, so you have 1 over L square minus m square plus I epsilon. Okay, and as I was saying last time, if you look at, you have 4 powers of L in the numerator and 2 powers in the denominator, so this diverges. Okay, I'll show you, as I promised, that I'll show you how to do it properly, but you roughly see that this is divergent. Okay, and this is the situation at one loop. Okay. The diagram, which is this, diverges. Let's see what happens at 2 loops. You have all this diagram, and others. So let's look at this one. Okay, I'm just doing it so that we get some practice with these Feynman diagrams, so that the later discussion becomes a little easier. So again, you have P entering. Okay, this is two loops, so you have two assignments of momenta. Let's call it L1. L1 enters here. L2 enters. L2 flows this way. So you have L1 plus L2 plus P in this propagator. Okay, and then of course P comes out. So this will, what will be the expression? It will have, first of all, because it's two loop, meaning you have two loop momenta, L1 and L2. Okay, convince yourself that you cannot have only one loop momentum here. It will not work out. Right? You will need two loop momentum, two undetermined loop momentum. So, but that is something you should check, that it cannot work without having two loop momenta. So D4L1, D4L2, and then you have all these propagators. L1 square minus M square plus I epsilon, and then you have 1 over L2 square minus M square plus I epsilon. Then you have L1 plus L2 plus P square minus M square plus I epsilon. Okay, I'm not being careful with the overall factors. I'm just writing the important parts. So you see, this one is also divergent. You have two powers from this factor, two powers of L from this factor, and two powers from this. So when all these L's are large, this will provide 6 powers of L. You can forget about this external momentum P and M, because they do not they are of no importance when L is very large. L1 and L2 are very large. So you see 8 powers in the numerator and 6 powers in the denominator. So this will diverge. Okay. And going to any other loop, the same situation. You will see that these are all divergent in ultraviolet. VIOLET. Okay, this statement means that when you take large momenta, this is divergent. This is also called as ultraviolet divergence. So you see that if you try to calculate this 2-point function to extract what the physical mass is, you don't get anything. Okay, because all these corrections are infinite. They are all divergent. So there is no prediction coming out from your theory. Okay, so even though this is very bad situation, it's hopeless, but just because I am drawing some diagrams and writing down some expressions, let's continue that, and even without any good motivation for this, I will just draw some diagrams and see what happens. Okay, what kind of diagrams there are. Okay, later that information will be useful. Okay, how about 3-point function? So I saw that 2-point function is ultraviolet divergent. How about 3-point function in 5-4 theory? Okay, if you remember, or maybe you can see now itself, that such Green's functions or such diagrams you cannot draw in 5-4 theory, because you have a vertex which has 4 lines attached to it. So you'll never be able to draw any diagrams which has odd number of external lines. Okay, so this is out anyway. Let's go to 4-point function now. So you have okay. So this will be plus this is one loop, and we have drawn already several times such diagrams. Let me draw them again, and then you have, I always find this drawing this last one confusing. Okay, so that's at one loop. I mean, you also have these ones and others, but these ones I will not consider, because when we were calculating S matrix, we saw that this after LHZ reduction was done, I could express the S matrix in terms of amputated Green's functions. So I will not include this one. I will include only the ones without any external corrections. Okay, and all the external corrections were in the Z functions or wave function renormalization constants. Okay, so let's see what we get here. Let's look at this one. So I will draw it again. P1, P2. Okay, let me tell you that here these momenta are like this. So P1, P2, P3, P4, and in this one also it's the same assignment. Because if you change the momentum assignments, then your diagrams will look different. Okay, I can just also draw all these three diagrams in exactly the same manner and change the places where P1, P2, P3, P4 appear. Okay, and then all diagrams will look the same. Okay, so what I'm saying is, if you take this one, here P1, P2, P3, P4, let's say you change the labels here. Instead of P1, you make, let's say, P3. So this one, if you change to P3, and this one to P2, P2, P3, then it is this diagram, right? Because at this vertex, P1 and P3 are meeting, okay? And at the other vertex, P2 and P4 are meeting. And that is what you'll get if you were to make this assignment. So then at this vertex, P2 and, sorry, I should have said not this way, but here P3 and here P2. Then it would be P1 and P3 meeting at this vertex, which is what is here, P1 and P3 meeting at this vertex. And then P3 and P4 meeting, P3 and P2 meeting at this vertex, which is what is here, P2 and, sorry, this is P3 and then this should be P2. I'm repeatedly making mistakes because this I leave as P4. So then P2 and P4 meet, which is here. Okay. So either you can choose to draw these diagrams like the way I have drawn, or draw the same diagram repeatedly but change the external momentum positions. But it's more convenient if you draw it this way. Anyhow, so at this vertex, P1 and P2 enter. Okay. So the total momentum that is injected at this vertex is P1 plus P2. Let's call it P. So I define it P as P1 plus P2. That is what enters in here. Okay, and then you have a loop momentum L, which I want to choose this way. Then you have L plus P flowing this way. Okay, and again let's write down the integral. It's d4L 1 over L square minus m square plus I epsilon, and then you have 1 over L plus P whole square minus m square plus I epsilon. So this is also divergent. 4 powers in the denominator and 4 powers in the numerator, and this is a divergent quantity. Okay, as you can see by this power counting. Okay, this will, if you were to put a cutoff lambda, it will diverge logarithmically. Okay, so no surprising, this is also bad. But let's move further ahead and draw a few more diagrams. So I have looked at already 2-point function and 4-point function and found that they are all diverging at one loop order. Let's look at 6-point function now. Okay, so you have sum of these two momenta, let's call it P1, it enters here. Sum of these two, let's call it P2, that enters at this vertex. And the sum of these two, let's call it P3, and it is injected into the diagram at this vertex. Okay, and let's assign momentum L like this, then it becomes L plus P1. This becomes L plus P2, and this is anyway L plus P3. Okay, so let's write down the expression, or at least the integral. d4L, it's one loop, so only one loop momentum. 1 over L square minus M square plus I epsilon, 1 over L plus P1 square plus I epsilon. Okay, so we have three denominators because we have three propagators. Each brings a power of 2. Okay, so we have a total power 6 in the denominator, and in the numerator you have 4 powers. Okay, so this is ultraviolet convergent because the function is falling sufficiently fast that in the limit L going to infinity, this converges. Okay, it doesn't diverge. So good for us, at least one diagram is finite, but that's not going to change anything because we still cannot determine masses, physical masses in this theory, or even 4-point scattering function. I mean, suppose you are looking at a cross-section calculation of 2 particles scattering to 2 particles, you cannot calculate it because it will come out to be infinite. Okay, because these diagrams are divergent. Okay, you might think that if you were to calculate 2 particles, let's say this and this, going to 4 particles, okay, 1, 2, 3, 4, this will come out to be finite, okay, because this diagram is finite. So lowest order diagram you can draw like this. 2, I hope I can find yeah, this one. So if let's say this one is, these 2 are incoming and these 1, 2, 3, 4, these 4 are outgoing, then this is tree level diagram. There are no ultraviolet divergences because there are no loops involved. So you can calculate this one, and then you look at this one loop which has turned out to be ultraviolet finite. So it looks like you can calculate 2 going to 4 scattering, okay, that scattering matrix element, and that will come out to be finite. And if you were to calculate cross section for 2 going to 4 scattering, you might naively think from this that it will come out to be finite. Okay, but that's not the case, and let's see why. And the reason is the following. So let's take this one again, which is convergent, and you understand why it's convergent, because now you have larger number of denominators. See, the numerator power is still fixed, it's d4L, so 4 powers in the numerator. And what we have done is increase the number of denominators by going to more number of external lines, so that the number of denominators has increased, and it brings 6 powers, so it is converging. But now when you are calculating cross section for 2 going to 4 scattering, this diagram will also contribute. Okay, but now this is this convergent? Well, you might think that this is convergent because you have 1, 2, 3, 4 and 5 propagators. So that brings a that brings 10 powers of L in the denominator. In the Feynman integral. And you have 4 powers in the, sorry, not 4. You have, so this is how many loops? This is 2 loop. Right? You see one loop here, one loop here. Or you can just try to also check the momentum assignment. So this is loop. Momentum, it goes here. It's determined by whatever momentum comes in from here, that adds up. Let me write it P1. So it is L plus P1. P2 enters here. So this is L plus P2. But at this vertex, this momentum you cannot fix, right? Because you have 3 lines going from here. So one momentum enters, and you have 1, 2, and 3 lines. You cannot fix momentum in all the 3 lines. So let's assign this one as L2. Okay, L2 flows in like this. And now this one is determined. Okay. And then you have this, and and this one more propagator. So you have 10 powers of L. And how many powers in the numerator? You have D4L1, D4L2. Let's call it L1. Let's call it L2. Okay, so 8 powers. So naively, it looks like this will be convergent, right? Because you have more powers in the denominator compared to the number of powers in the numerator. But then when you are doing this integral, okay, this, see here, let me just write here, it is L1 plus P2 in this. Because this cannot change the momentum that has that is going out. It will just be the same. So you will have D4L1. Let me write it down. D4L1, and then all these propagators which have only L1, and then this one D4L2, and this will be 1 over L2 square minus M square plus I epsilon. Okay, somehow it has stopped working. Okay, so this now look at this one. Even though the way we are counting it looks like it's finite, but if you look at this piece which is multiplied here, this is ultraviolet divergent, right? We have already seen this because this is ultraviolet divergent. So you have a divergent piece in here, and this is called a subdivergence. Okay, so the diagram looks like, if you do just a power counting, it looks like UV finite, but it has a subdivergence sitting in it. This is UV divergent part. So our hope of getting 2 going to 4 scattering as a finite thing in this 5-4 theory, even that is gone. So there's nothing that we can really calculate in this theory if we were to proceed the way we have set up things right now. Okay, so what should we do next? And what's the, you already know that people do quantum field theory and they get predictions for scattering cross sections at these different machines that we have built over time, like large electron positron collider or tevatron or LHC. So clearly we can get some finite results. Okay, and the thing that makes it possible to have finite predictions from this theory is called renormalization.